Woohoo, and welcome back. We're talking about 9.1 again, but this time we're going to continue on and work in a more practical sense. When we last left our heroes, we were working with very theoretical perspectives on limits. And now, first off, I think I'm going to turn off this side light so that I can cut down on some of the glare and the shadows. And then we're also going to be working in this page. Now, this page looks a little different than in your notes, and that's because I decided to color code everything. I've got my support sea carnivore right here. Sharktopus is joining us to be supportive, woohoo, and root us on. Mostly because you can see this graph that I've got drawn looks a little bit like waves. It's a really unusual graph. You may not have seen a graph like this anytime recently, or maybe even ever, because if you look at this graph does some really interesting things. And I'm wishing I had a little pointer stick, which I don't. So I'll go ahead and use my pen. So the graph starts over here, it goes up in a hump, and then it stops. And then there's a big jump, and then it starts up here with an open point. That means the point doesn't exist here. The point exists up here in the closed point, the filled in point. And then it goes up and then down like a wave, and then it stops at this closed point. And then there's another jump to an open point, and then it goes up and then back down again. So this is doing some really interesting things. You can imagine this could be a model for a particularly rocky week in the stock market. Stock market does go up and down, and sometimes what happens with the stock market is there will be trading, and then trading will halt overnight, and then in the morning trading might start low and go up, and then there's some bad news, and then this is the close of trading, and then first thing in the morning, bam, it's up high because there's some good news overnight, and then it goes up and it comes down. So you could imagine this isn't that far off for a reasonable graph. It's just this graph is not easy to study. So you haven't seen a lot of graphs like this yet. The reason I'm picking this graph right now is that it's really great for helping us understand limits, because it gives me a chance to show you lots of different possibilities for what's happening with the graphs and what's happening with the limits and all the fun stuff. So let's go ahead and get started. I've got these three, there are four different colors. These three, if we look carefully, we see we have a left hand and a right hand and a two-sided limit all around 2. X is approaching 2 from the left, X is approaching 2 from the right, X is approaching 2 from both sides. And I'll remind you that left is, oops, let me get this all the way on the screen. Left is on this side. Do not laugh. This is not obvious for everyone. Left and right is a tricksy thing. I spent years trying to figure out which one is left and which one is right and trying to remember it. So left is over here, and we'll see that when we see an arrow and a 2 or whatever the number is and a minus. It means we're going from the left-hand side, from the smaller numbers. And we're coming in from the right side if we see an arrow with a number and a little plus. And the goal is that as we come in from the left and the right, the two meet. And if they meet and they agree, then we've got a two-sided limit. If they come in and they don't agree, then we don't have a two-sided limit. We have a left-hand limit over here and a right-hand limit over here, but there's no agreement. And you can already see that if you look at this graph, there are going to be a couple points where we just don't have any agreement there. So let's go to pink land, and pink land happens around X approaching 2. So here I've got my vertical line right here at X equals 2. Right there. Oh, I'm not sure that's going to be as helpful. Let me try using my purple. I don't like that as much. I'm going to go back to this one. So when X equals 2, There's my x equals 2, and you can see I drew a pink dotted line right there. And so first we want to ask, what is the limit as x approaches 2 from the left, from the smaller numbers? So what we do is we're thinking x is coming in this way, but we have to ride on the graph. We're not riding on the axis, we're riding on the graph. So as I go along here, I'm going and then back down and bam. And it looks like I'm approaching this point. Now, when you answer what a limit is equal to, you give the y value. So what's the y value at that point? -1. So this is -1. Oops, there we go. And all of these answers here, well, these two at least, these will be y values. So answers to limits will be the y's. Where do the x's go? The x's tell you where you're going to approach. Okay, so now y approaches 2. The limit as x gets closer to 2 from the right, so it means from over here, we're going to ride the graph up and then bam, we end up here, which is the y value is 5. So those two are y values. And so what's the two-sided limit? And the answer is, it doesn't exist. There's no agreement. So if you remember from yesterday, D, N, E does not exist. And I said yesterday, it might have been 10 minutes ago for you. I don't know. Time works weird in YouTube land. Everything is time travel at this point because I'm talking to you from the past. Ooh, spooky. So you know stuff about the really interesting thing is when you're watching this, you will know things about the stock market that I don't know when I'm recording this. You might know things that could have made me right now as I'm recording it a billionaire if you could have told me, but sadly you are in the future and I am in the past now. So, okay, so much for that. So much for the get rich quick scheme. There we go. Okay, so if the two sides do not come to agreement, we don't have a two-sided limit. That's all. That's all that is. Let's go to blue land. All of these three center around x approaching -1 from the left, x approaches -1 from the right, and x approaches -1. No plus or minus means both directions. So here's blue land. There's x equals -1 right there, right along that line. So as we go from the left, the limit as x approaches -1 from the left, we go whoop, and the y value is 4. Okay. The limit as x approaches -1 from the right along here, and we end up, oh, that's interesting, we end up at the same point, also 4. So if we've got these two coming together and they meet, if those two are equal, the two-sided limit is 4, right? So if these two agree, if these two are equal, then we get a two-sided limit. Woohoo! That's very exciting. So in other words, this point, the two sides of the graph meet. Yay! And it happens to be a point on the graph, which is even better, more exciting. So now let's go to Greenland. So what's the limit as x approaches -4 from the left? From the left means over here. Whoop, and we end up right there. We ride on that graph, and that's 3. Now from the right, coming from over here, we ride the graph down here. We end up at this point, which is y equals -2. Okay, do they agree? And the answer is no, and we can see that because there's this big jump. So this does not exist. But I want to do one more thing. I want to ask you, what is the actual value of y when x equals -4? It's a fair question. And the answer is, when x equals -4, we're in that green line, when x is -4, we've got two possibilities. it's this one where the point is filled in. That's the closed point. That's the point that exists. This one, the open point, doesn't really exist on the graph. Now, why can't they both be filled in? Why can't they both be closed? We'll do this Dora style. I'll pretend you're giving me answers. You're right! They can't both be filled in because then it wouldn't be a function. Remember, the basic rule of a function is a value of x in gives you one value of y out. So when x equals -4, what's the answer? The answer is that the point is right there. So it's at 3. So in my mind, 3 wins a little bit more than -2 does. But that's just because I'm imagining, cage matches between all the numbers when they're fighting it out. Let's go to purple land. Purple land is right here when x equals +4. Now, x is approaching 4 from the left, so let's come from the left side. Oops, sorry, got too excited. And let's see, that y value is 2. Awesome. The limit as x approaches 4 from the right, let's come up. Oh, also 2. Yay! Do the two sides of the graph meet? Right there? And the answer is yes, they do. The graph meets. The limit exists. So what is g of 4? G of 4 is probably 2. And if you said, we don't know what g of 4 is, you're right. Notice that that point is missing. And there's no filled in dot anywhere that we can see. Now, there may be more of a graph that I just didn't show you. There may be more something else that I didn't include here. But from what we can see on this page in this graph, this is undefined. And again, does undefined mean something bad's happened? Not necessarily. It just means we haven't been told. Literally, we have not been told what the answer is. The answer is undefined. So we've got a lot of different possibilities, and these are all really important aspects to calculus. Again, I'm going to remind you that I'm hitting the theory really. I'm really trying to give you a nice solid foundation, because I know that some of you, when you go on to get your MBA, are going to have to take a full course of calculus. And so I want to get a little bit extra into your head so that when you do take calculus in another class, you'll be like, oh my gosh, I remember this. And it'll make it go just that much more smoothly, rather than only giving you the superficial stuff that, is honestly what the book wants you to learn. Okay, so this is graph-based limits. Okay, we did theoretical. That was this page. All the words. It's theory when there's a lot of words. Then this is the graph-based because, there's a graph. Okay, next up, algebraic. And if you peek, you can see, oh wait, there's a graph. There's another graph back there. Yeah, mathematicians don't go far from graphs when it comes to calculus. Calculus and graphs are seriously... Calculus and graphing are sitting in a tree, K-I-S-S-I-N-G. If you ever sang that little song, yeah, graphs and calculus, my gosh, just the best of friends. Totally gonna get married. Okay, so what are we doing here? Well, now we're going to approach the concept of evaluating a limit without a graph. And I know you guys are like, but there's a graph down there. And it's like, yeah, but that's for the last one, because we're gonna hit a problem, then we're gonna have to look at a graph. But for the most part, if someone asks you, what's the limit as x approaches 3 of 2x squared minus 3x plus 4? Well, we could graph this. And we could do the thing where we look from both sides, see what happens when x approaches 3 from the left and when x approaches 3 from the right. But there's some theory. And like I said, we're not going to do all the theory. We're just going to do some of the theory. But there is this theory that says, it's a theorem, it's true. It says that if the limit exists, if the limit is defined, if basically nothing goes wrong, the limit as x approaches 3 is whatever happens if you just plug in 3. Now, tell me about how lovely parabolas are. Think about parabolas. Think about polynomials. This parabola, smiley face, right, opens upward. No holes, no jumps, no jiggity jaggedy stuff. It's just a nice smile. So it's well behaved. So when we get a situation like this, we just plug in the value. So it's going to be 2 times 3 squared minus 3 times 3 plus 4. Literally, we're just going to plug that 3 in. Wherever we see an x, we're going to put, oops, right there, put the value of 3 in. So let's see, this is going to be 2 times 9 minus 9 plus 4. So that's 18 minus 9 plus 4, which is 9 plus 4, which I think is 13. The one downside of us be recording it ahead of time means that I don't have a classroom full of people who can help me when, my brain goes a little sideways. But I believe it's 13. Woohoo! It's really, it feels like cheating. It always felt like cheating to me, but it's just a wonderful result. If the limit exists and it's well behaved, then you just plug in the value. Okay, so next up, dum dum dum, the limit as x approaches 3 of 2x squared minus 3x plus 4 all over 2x minus 3. Oh no, this is so complicated. It's the end of the world. And the answer is, it's really not the end of the world. Because if I plug in 3, we already knew, look, I don't know if you noticed. Look at that. Same exact polynomial up there. We already know that 3 causes no problems in a parabola. Parabolas are really easygoing. That's why we study them, kind of lines and the parabolas. They're really easygoing. Nothing upsets them. So everybody's cool up there. Now, when you do have a rational expression, sometimes the denominator turns to 0 and then the whole thing collapses. It's the end of civilization as we know it. But the good news is 3 is not going to do that. If you plug in 3 in down there, you're going to get 2 times 3, which is 6 minus 3, is still 3. It's not 0. So as long as you don't have a 0 in the denominator, you're golden. Literally. Sorry. Sometimes when I'm doing math, I have to be very quiet. Otherwise, my hand goes and writes things that I don't know. It tries to wing it, and it's not a good idea. I am not a bird. So I plug in the 3 everywhere there was an x. X, 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 X. Everywhere there's an x, I plug in a 3. So I get 2 times 9 minus 9 plus 4. I mean, I could have just copied this down here, but I'm going to work it out again. 2 times 3 is 6 minus 3. So up on top it's 13, down on the bottom it's 3, and that's my limit. So literally it's just plugging in numbers, which is like so wonderful. It's the best. It's awesome. Super dance party time. Okay, now dance party is over. Now everyone needs to sit down because notice the last one. The limit as x approaches -2 of x over x plus 2. Well, if we're having our dance party, we're like, yeah, this is super easy. Life is good. I'm just going to plug in the -2 wherever I see an x. So it's 1 up there and 1 down there. And so I get -2 over 0. Oh no. Oh no. So the rule is, if you can plug in the value and nothing bad happens, you're golden. So this is kind of like an ask. Rather than asking permission, it's just apologize after the fact. So try it, and if it blows up, then you're like, oh no, that's undefined. And the problem is we haven't, as a class, studied limits. I mean, heck, this is like your 5th example. So no, we haven't studied limits very much at all. If we were doing this, if this were a full semester calculus class, we would spend at least a week on the limits. Personally, I would. I really feel like it's important to be really solid with what a limit is. And so, like 45 minutes is not going to hack it. So we don't know what's going on, except that it blew up, civilization is falling. And so, after a slight technical difficulty, I'm going to show you, ta-da, the graph. This is the graph of this function that we're looking at, x over x plus 2. And we're interested in what's happening right next to -2, right around there. So let's take a look. You can see I've got my y-axis marked in. I've got my x-axis. You can't see it, but it's there. And you notice that some really interesting stuff is happening. This turns out to be a really cool function. It's got like 2 different wings. It's got this piece right over here, and it's got this piece over here, and it's split right along the x equals, right here, x equals -2, right along this vertical line. And so you can see what's happening, and why everything kind of blew up here was that from the left side, the function gets really big. And from the right-hand side, the function gets really small. And hopefully, if you've studied some other algebra classes, maybe studied some more graphing, you know that this is asymptotic. So this is going to keep going. This can get real close to the line, never quite touching it, but it just goes up and up and up forever. And this one's going to come down forever. And so the question is, do the left side and the right side agree? And the answer is no. Now, this side is going up to a very big positive number, and this side is heading down to a very, depending on your perspective, either a very small number or a very large in magnitude negative number. And so there is no agreement. So the limit does not exist. Okay. So here we had to actually look at a graph. And again, if you do decide to go on to a calculus class, a full semester calculus class, there will be other tips and techniques to help you through situations like this. Okay, so we've got those. And then let's take a look at what happens next. So what I did want to talk about was, what if you have a situation where a function goes up and up and up and up, or down and down and down and down? What happens when you're looking at very big numbers or very big negative numbers? What happens? So we're going to look at infinite limits. So the problem we're going to start with is find the limit as x approaches 0 of 1 over x squared if it exists. So if we're not in the DNE situation. Okay, so first thing we try is just plugging in. What happens when you plug in 0? 1 over 0 squared is 1 over 0. That's undefined. So off the top of our heads, we don't know what's going on. It's exploding. Bad things are happening. So let's take a look at what's happening close to 0. So what I want to do is I'm setting up another one of these charts. I'm going to go ahead. Ooh, I found this calculator. Very exciting. You can use any calculator you like. If you do happen to have a graphing calculator, you can set up charts more easily. Or you could do this in Excel. You can set it up in a lot of different, or Google Sheets. So let's try all these values. Now, the first question that I'm asking here, why can we use plus or minus? So in other words, I'm not looking at +1 and -1. I'm looking at both. plus or minus 1? And the answer is because I'm squaring it. So it doesn't matter whether I put in a positive 1 or a negative 1, I will get the same result, right? Because when you square a number, it doesn't matter whether it started out positive or negative. So I'm going to switch places with my calculator. Let's see if I can kind of put this in over here. Oh, try not to blind everyone. Nope, can't do it. Okay, you're going to have to take my word for it. You won't see me doing a lot of this, but I will write down the results. Okay, so if we plug in 1, I get 1 over 1 squared, which is 1 over 1, which is 1. Okay, so when x is 1 or negative 1, my result will be 1. Now, if I go to 0.5, 1, oops, I'll show you one of these so you can see it. There we go. 1 divided by 0.5 squared equals 4. Okay. Now, why is that? Well, 1 over 0.5 squared is 1 over 1/2 squared, which is 1 over 1/4. And remember, when you've got a fraction in the denominator, it flips up. 1 divided by 1/4 is equal to 1 times 4 over 1, which is 4. So that's interesting. We went from 1 to 4. And again, if I used negative 0.5, so if I had used negative 1/2, I still get 1 over 1/4, which is going to be equal to 4. Since I'm squaring it, the negative gives the same value as the positive. Okay, so we can guess 0.2 is 1/5. So if we're going to square that, we're going to end up with 25, right? But let's double check. Again, avoid the ring. Stay out of the ring, Carol Ann. Okay, 0.2 squared, 25. So I get 25 here. Okay. 1 divided by 0.1 squared is 100. 1 divided by 0.01, the quantity squared is, this is 10,000. 1 divided by 0.001 squared is, and then I'm going to parse this. There's 3, and a 1. That's 1 million. So what's happening? As x is getting smaller, closer to 0, or if you're looking at the negatives, getting bigger and closer to 0, what's happening to my y values? They're going pew, getting really, really big. So look at the graph on Desmos or another graphing app. And again, if you haven't actually tried it, because some people are like, what the heck is Desmos? Just Google Desmos. It's a free online graphing calculator. It is slightly more user-friendly than trying to graph things on Google, but Google will also graph things. There are a lot of other graphing apps, but Desmos is free, and the organization is dedicated to, education. So they're not sneakily trying to sell you something. Okay, here's the graph. So this is the graph of 1 over x squared. And again, there's my y-axis. This right here, this is the x-axis. This is the y-axis. And right here is where x equals 0, along this line here. And what's happening from the left side and the right side is, now, are they meeting in the middle? No, they're both heading up. Forever and ever and ever and ever. Forever. It's another situation with asymptotes. So what do we say the limit is? Because they're not stopping. We can't say the limit is 70 or 80. The limit in this case is f of x keeps getting bigger and bigger as x approaches 0 from the left and the right. And in this case, we say the limit as x approaches 0, two-sided limit, is infinity. It's kind of cool. It is unusual to see equals infinity in math, because a lot of times, hopefully up until this point, you've been taught infinity is a concept. It's not a number. You can't set something equal to infinity. But the limit, and remember, the limit has to do more with where something is headed than where it is equal to, right? It's where the tendency is going. That is infinity, which is another way of saying it gets large without bounds. Now, why did I pick 1 over x squared? Well, 1 over x squared, both sides go up, so we have agreement. Remember the previous one, we had this one where they went in opposite directions, so that we don't have agreement. Okay. Now there's a little bit more. Again, this is theory that we aren't going to use a lot of in this class. But again, I want to give you that full experience of calculus, even if we can't quite get to everything. Here's the definition. Let f be a function defined on both sides of a. So we can go from the left and the right, except possibly at a itself. Remember, for a limit to exist, you have to have both sides agree, but you don't have to have a point in the middle. Then, the limit as x approaches a of f of x is infinity, means that the values of f of x can be made arbitrarily large as we please. So arbitrarily large means you can set any standard, and I can find a point where that's true. So what does that look like on the graph? Well, so for example, basically what we're trying to do is we're trying to define infinity for mortals. So we as mortals, as folks who will eventually die, can't really experience infinity personally. We can think about it, we can conceptualize it, but anything that we experience in our lifetimes is mostly going to be finite. Time or the amount of things we can see. We have the concept of the universe, so you can imagine something that extends forever. But as humans, I'm not sure how much we can actually hold on to. So because of that, we have to come up with what does infinity mean? And so what mathematicians have decided, and this is part of why I wanted to include this, because I think this is cool, is the definition for us. The way we grab onto infinity is by saying something, the limit approaches infinity, it increases without bound. You can pick any number you want. You say, fine, 10. I say, great, they both get to 10 here. So as long as I am that close to 0, my values become 10. Okay, and then you could say, no, 80. And I say, great, they get to 80 here. So I can find, I don't know what those values of x are right there, right? That positive and negative value that gets us to y equals 80, but I could find it. No matter how big a number, you could say 10 million. Well, I'm going to need a big graph, but I can get it. I can get to 10 million up there. And as you recall, to get to 1 million, if you had said, okay, you got to get to 1 million, I say, okay, pick these x's will get you to 1 million. So in other words, no matter how big a number you pick, I can find the x that gets you there. That's how we define a limit being equal to infinity. It's pretty cool, I think. So what did I write here? Plainly speaking, this means that a function that keeps going up and up and up without stopping has a limit, which is a weird thing to say, equal to infinity. If the function stops, if it does not continue to go up and up, then the limit is not infinity. The limit is something finite. And then here's the thing. There are some mathematicians who are like, you cannot say the limit is infinity. That's contradictory. So some texts say the limit does not exist, meaning there is no limit. It keeps going on, getting bigger and bigger forever, if that makes sense. Some texts say it does exist and it's infinity. And I'm sure it would be entertaining to get two of those mathematicians into a room and just close the door and listen to them like "Rrr," like two feral cats. Um, but what I'm going to say is what this book likes is we say the limit equals infinity, which is going to work just fine for us. So that's it. You guys made it. Dance party time. Dance party. Oh, I don't have another. Where's my planet? There's my planet. Planet 9. Planet 9 dancing with Sharktopus. I hope you guys have a great time. Whatever you're doing after this, I hope you get some rest, some hydration, some snacks, some sleep, some exercise, vegetables, maybe even some sunlight or fresh air. Woohoo. Know that you're amazing and awesome. And if you want to talk about any of this with me, please don't hesitate to ask. I would love to help it make more sense. And we'll go on next to 9.2, which is another building block of calculus called continuity. Woohoo! Okay, I'll see you guys then. Until then, woohoo and math on.